Assalamu alaikum wa rahmatullahi wa barakatuh. In the name of Allah, the most gracious, the most merciful. Today, inshallah, Rabbil Alameen, we will talk about Chapter 7, Section 3, Kepler's Laws. Generally, this section is talking about the motion in space. And the beginning of this session is Kepler's laws. So let's know what does Kepler's laws, this term, mean. Kepler's laws are, as you see in front of you, are three laws. Those describe the planetary motion. So these laws describe the planetary motion, the motions of the planets in space. Before saying anything, this law is not accurate, okay? But it's one of the respectful, the respected stations in the history of physics, okay? But please don't use it as if it's fact, okay? No. They were developed before Newton's law of universal gravitation, and there were more than one theory before it. Well, Newton used them to support his new laws of gravitation because of some deviations of some planets. These planets, when they make some deviations in their paths than the expected, that shows there are planets beyond them, okay, and so on. Many observations of these laws also supported Newton's law of gravitation. Well, now inshallah, we will begin with this point. Sorry. The first law, there are three laws, by the way. There are three laws. The first law is called Kepler's first law, or the law of planetary orbits. So this law just describes the shape of the planetary orbit. Okay? This law says each planet travels in an elliptical path. Mr. What's meant by elliptical? Elliptical means ellipse. It's not circular, okay? It's some circle, some pressed circle, if it's correct to say that, okay? It's as shown in the figure. The ellipse is that shape. This is the ellipse. It's not circular. It's not circular, okay? But it seems to be, or it seems as if it's overlapping of two circles. So it has two centers. So it has two centers. Each center called focus or focal point. So these two centers are called two foci. Well, so where is the planet here? The planet is rotating in that elliptical path, okay? Well, where is the sun? The sun is in one of these two foci or focal points. So this law, it's so easy, says each planet travels in an elliptical path such that the sun is at one of its path of its foci, okay, and the planet is rotating in this elliptical path. So if I ask you if the path of the planet is identically circular, no. It's according to Kepler's laws, it's elliptical. Well, this is the first law. The second law is called Kepler's second law, or the law of areal speed or sector velocity. So it's called the law of areal speed or sector velocity. You can memorize Kepler's second law. Okay, well, what does it say? It states the imaginary line between any planet and the sun sweeps equal areas in equal time intervals. So what does it mean? To understand what does it mean, let's see the following. Let's clear the figure and sketch another one. This is, now I'm drawing the elliptical path. Okay, here the planet is rotating. It's in this point. Here, this is the sun. If we imagine that we have a line here like this is called the imaginary line between the planet and the sun. This is the imaginary line. When the planet becomes here, this line becomes here. When the planet becomes here, this line becomes here. When the planet becomes here, this line becomes here. Well, the law says that this area that's swept by the imaginary line, and this area that's swept by imaginary line. If I tell you that, for example, if I tell you that this, let's make the planets here to be more if we imagine that these two areas, this area, it's made in certain time, which is, let's say, 2 months, for example, okay, delta T. And this area is swept by the imaginary line in the same, in equal time, yani, another 2 months, okay. The law says this area will be equal to this area. Mr. How? Mr. This triangle has larger height, yes, but it has smaller base. And this one has smaller height, but it has larger base. Generally, that law says that this imaginary line sweeps equal areas. This imaginary line sweeps equal areas in equal time intervals. Well, that involves something important. What is it? That involves the planet when it's in the closest point of its orbit to the sun. What does it mean? For example, here, this is the orbit of the planet. When the planet is here, it's at the farthest point in its orbit, okay, from the sun. It's too far from the sun. When it rotates to reach this point, it will be here in the closest point to the sun. To satisfy this law mentioned by Kepler, that means any planet moves faster in the orbit here when it's close to the sun in its orbit. I'm talking about one planet. Here, this law is talking about one planet. It doesn't talk about two planets. One is closer than the other. No, this is talking about one planet in its orbit. Sometimes it's close to the sun, and other times it's far from the sun. When it's close to the sun, it moves faster. When it's far from the sun, it moves slower to satisfy that condition or that law, which says that imaginary line between the planet and the sun sweeps equal areas in equal time intervals. I hope it's clear. Well, this point is very important, and inshallah, I mean, it will be one of the components of the attendance quiz. Well, now let's talk about the third law, Kepler's third law. This is the third law of Kepler and the last law of Kepler. Kepler's third law is talking about the year of the planet. First of all, let's know what's meant by the year of the planet. The year of the planet is called the planet's orbital period, and have the symbol capital T. We will explain the previous board now, okay? But before anything, let's know that the planet's orbital period is called the year of the planet. For example, if I tell you that the planet's orbital period of the sun is T, it will be what? 365.25 days, or 1 year, 1 Earth year. This is of the Earth. In case of what? In case of Earth. Well, so the planet's orbital period, capital T, it's equal to any year of this planet, and it's the time needed to make one complete orbit around the sun by the planet. I hope it's clear. Okay, well, so now let's come back to the law. The law says the orbital period of the planet, which is T, which is the year, to the power of 2, yani the square of the orbital period to the planet, is directly proportional to the average planet-sun distance of 3. The orbital period of any planet, it means the year of the planet raised to the power of 2, T squared, is directly proportional to what? To the distance between the planet and the sun, and it will be more accurate to say the average distance between the planet and the sun raised to the power cubed, which will be given the symbol r cubed. Okay, Well, so this is the statement of Kepler's third law. Again, the orbital period of any planet, the time of the year of any planet, raised to the power of 2, t power of 2 is directly proportional to r power of 3. T power of 2 is directly proportional to r power of 3. Okay, well, it means T represents what? Represents the orbital period or the year, the time of the time needed to complete a year on the planet. This is or the distance between the planet and the sun, and it's called the planet-sun distance. Well, so we can, to solve the problems, we can write this proportionality t, we said t to the power of 2 is directly proportional to r to the power of 3. So if we have two planets, we can write that t2 to the power of 2 divided by t1 to the power of 2 equals r2 to the power of 3 divided by r1 to the power of 3. Mr. From where we got this? From this formula. We said if y is directly proportional to x, it means y2 divided by 1 equals x2 divided by x1. That we did here. But here we have powers, so we put the powers. So this is for two planets 1 and 2, okay? And this formula says that t squared with r cubed will be a straight line, starts from the origin, okay? But by the way, close to the origin, we will make dotted line. Why? Because there is no planet at distance 0 from the origin, from the sun. Well, now, note that Kepler's third law shows that as sun-planet average distance, which is r, increases, the period of the year increases. So if I ask you which planet have longer year, again, the question, if I ask you which planet has longer year, the Earth or let's say Saturn, which one has longer year? Can you answer me? Which is farther from the sun? Yes. Okay. The answer will be that Saturn will have more year or longer year. Why? Because it's farther from the sun. Because it's farther from the sun. Well, in problems of third law, use r, which is the distance between the sun and the earth, equal 1 AU. What's AU? AU is called astronomical unit, and it equals the distance between the earth and the sun. It's approximately equal 1 . 150 million kilometers. Well, use the, you don't have to memorize this. You don't have to memorize this. Just memorize this. The distance between the Earth and the Sun is called 1 astronomical unit. 1 astronomical unit. Use the time of the year of the Earth is 1 year, 1 year, 1 Earth year, 1 Earth year, year here means Earth year, or 365 days. Well, now let's talk about the AU, the astronomical unit. It's the average distance from the Sun to the Earth, and it equals approximately 150 million kilometers. It's 149.6, by the way. This is the accurate number. Okay, let's have this example. Find the year on a planet whose average distance from the Sun is 4 AU. Well, so he's asking about T of the planet, which is T2. Okay, and he gives us the distance of the planet, which is 4 AU. Well, and we know it's given, or it's memorized. It's as it's, or as memorized, as memorized, as if it's given that T of the Earth, so we will take the Earth as the other planet. Here we need 2 planets to compare between them. He's asking about 1, so we will make the other one is the Earth, the another one is the Earth. So T1 equal, T1 is the time of the Earth. It's 1 year, 1 Earth year, okay? And the distance of the Earth, which is R1, will be 1 astronomical unit. It makes the problem so easy. So we will put the formula here, T2 divided by T2 squared divided by T1 squared equal R2 cubed divided by R1 cubed. T2 is an unknown, okay, so it will stay T, okay. T of the Earth is 1, R cubed is 4 cubed, so it will be 64, then and the R of the Earth is 1, so simply T squared equals 64. By taking the square root of both, we will get T equal 8 years. So it's a piece of cake. Okay, so this is the third law of Kepler's. Okay, so we finished Kepler's 3 laws. Now we will talk about the last point in this chapter, which is the weightlessness. Let's remember the following. We studied that the weight is the magnitude of the gravitational force acting on the object. And we differentiated between the weight and the mass, and we said the weight is measured in newtons and the mass is measured in kilograms. The weight is dependent on location, so it varies from a location to another, but the mass is not dependent on the location. If there's no factors affecting the mass, it will stay constant anywhere in the universe. Well, we know that the weight is equal to the mass times the free fall acceleration. All these are elementary points with respect to you. Okay, so the weight is on the Earth is more than the mass. The weight on the Earth is more than the mass. Well, now we will talk about the new point here, which is the bathroom scale. The bathroom scale. You know the bathroom scale? The bathroom scale is the scale or the balance that you are standing on it to see your weight. Okay? To see your weight, you are standing in front of some kind of balances or scales. Okay? This balance is called the bathroom scale. Okay? Well, this scale measures what? Give me a moment, please. Scale. Yeah. This is the bathroom scale. I'm searching for a suitable image. To show you the bathroom scale. Okay, I know. Okay, this is a bathroom scale. Okay, this is the bathroom scale. Well, now inshallah, we will go back to our presentation. Well, when you are standing on the bathroom scale, if I ask you, what does the bathroom scale measure? you will say, Mr. It measures my weight. In fact, this is not accurate. It doesn't measure your weight. It measures the it measures your weight because when you are at rest, the weight equals to the normal force. Mr. We cannot understand you well. It doesn't measure weight. Look at the pointer. So it measures what, Mr.? It measures the normal force. We know that when you are standing on the surface of the balance, we have two forces. The first one is your weight is downward, and the second one is the normal force is upward. When you are at rest and the balance at rest, the normal force equals to the weight. So in fact, it measures what? The reading of the balance is what? Is the normal force. The reading of the balance represents what? Represents the normal force. But because you are at rest and the balance at rest also beneath your feet, okay, this normal weight equals to the your weight. So if balance is at rest, it measures your weight because Fn equal Fg. I hope it's clear. Is it clear? Is it clear? So again, because this will be a very important question in the exam, inshallah, and the attendance quiz. Okay? If I ask you, what does the bathroom scale measures? It measures what? It doesn't measure directly your weight. It measures the normal force of the balance on your body. But because you are at rest, you and the balance at rest, okay, so the normal force is equal to what? Is equal to your weight, okay? So you can consider that the balance of you, the reading of the balance is the weight of you, or your weight. Well, but now, what will happen if you and the balance are moving up or down with an acceleration? With an acceleration, this is a very important point. It means the condition that I'm talking about now is that you and the balance, for example, in an elevator, you and the balance, we put the balance in an elevator and we make you stand on the balance in this elevator, and we make the elevator moves up with an acceleration, or down with an acceleration, not uniformly. What will happen? In fact, there will be additional force here. There will be additional force related to or due to the acceleration. Well, if this acceleration is up, that means the elevator that contains you and the balance is moving up. Okay, like this. Now this is the balance. And this is you. You are now in an elevator. If the elevator is at rest, the reading of the balance is Fn, and it equals to Fg. They are equal. What is the reading of the balance? This is the reading of the balance. Good. But if the object moves, if this elevator, this is an elevator. If this elevator accelerates up, the Fn, if this elevator accelerates up, the Fn will be not equal to here. طيب خلاص دلوقتي we are at rest. Now we are at rest. If the elevator accelerates up, Fn will be not Fg only. Fg is your real weight, by the way, remember. No, it will be Fg plus the acceleration due to that. Due to what? Due to that. Due to your plus the force due to the acceleration. So the reading of the balance will be more than your real weight. So if you are in a car and this car is moving up on a bridge, for example, it's moving up the bridge. What do you feel? You feel that you are heavier. If you are in an elevator and this elevator is moving up, what do you feel? You feel that you are heavier than your real. This feeling takes parts or fraction of the second, okay, during the acceleration. Well, but when the elevator moves down, you feel what? You feel what? You feel lighter than. When the car is moving down a bridge, you feel lighter than your real weight. You feel something like that. Okay? Well, why? Because the opposite will happen. If it's moving down, the Fn equal your weight minus ma, such that the a is the new acceleration of that you're moving with. Well, so if any object that accelerates up or down, it behaves as if it's on a bathroom scale on an accelerating elevator or in an accelerating elevator. Okay? If it falls or accelerated down with acceleration which is not equal to the free fall acceleration, the Fn will be Fg minus ma. It means the reading of the elevator of the balance will be less than your real reading. Okay, so the apparent weight will be less than your real weight. What's my apparent weight? Your apparent weight is represented by the reading of the scale. It's not your real weight. Your real weight is your mass, which is constant time the acceleration. Okay, but when you move down, you feel you are lighter. This feeling represents your real weight and can be measured by the balance, the bathroom scale. Well, if the object is falling freely, its acceleration equal g. In this case, the apparent weight will be Fg minus ma, or minus, and the acceleration equals g, so it equals Fg minus mg. Remember that mg is equal to your weight, so mg is equal to Fg, so they will be cancelled, so it will be 0. So the apparent weight of u will be 0, or the object will be 0 if it falls freely. So the rule here, falling freely means apparent weight weightlessness. It's not real weightlessness because there is weight, but it's apparent weightlessness. It means the body that's falling freely feels as if its weight is zero. So if someone has a bottle of water partially filled, and this one is falling freely, you will find the water inside the bottle is moving up. Inside the bottle is moving up inside the bottle, as if he is in a space shuttle and carries this bottle of water. Well, if the elevator accelerating up, the apparent weight will be more than the real weight, as we explained. Note that the apparent weightlessness, it's the situation where the apparent weight equals zero, okay, not the real weight, apparent weight. Apparent weightlessness and real weightlessness, what's the difference between them? Apparent weightlessness, where apparent weight equals zero, but the real weightlessness is when the real weight equals zero. The real weightlessness, it happens only in the absence of gravity, and these approximately happen in deep space, okay? But the apparent weightlessness, be careful, this is very important point. It's for falling free falling objects and the astronauts in orbiting space shuttles, okay? So if I ask you, is the weightlessness of the astronaut in a space shuttle is a real weightlessness? No, it's not real weightlessness. He is in an orbiting object, which is the space shuttle, and this orbiting object has a weight. But all what happens, the orbiting space shuttle is falling freely. We said that in the beginning. Anything that's orbiting, it behaves as if it falls freely. Okay. Well, so the astronaut feel or undergoes apparent weightlessness. Inshallah Rabbil Alameen, the next period we will finish our portion, inshallah, by studying this part, which is talking about the torque, inshallah. Thank you, everyone. Inshallah, I mean, today there will be an attendance quiz at 10:30 p.m. inshallah Rabbil Alameen. The link will be, it will be based on this video only. The link will be valid for 24 hours. Okay, revise the video well. If you have any question, send me your question on the group. Okay, and inshallah Rabbil Alameen, I hope you will do well, inshallah Rabbil Alameen, in the exam. Thank you, everyone, and have a nice time.